So welcome everybody to this evening's BMS Talk. Thank you for joining us. I'll start off by introducing our chair for this evening. Alexandra Dombrowski completed her MSc in Plant and Fungal Taxonomy, Conservation and Biodiversity through Kew and Queen Mary University of London, and she's currently a curator in the Fungarium at Kew. Thank you, Alex. Hand over to you.
Thank you, Sally, and good evening to everyone. Welcome to the BMS Talk for June. Tonight, I'm really excited to hear all about Hebeloma from Henry Beker. Really quick before I introduce him, I'd just like to say that if you have any questions during the talk, please pop them into the chat. I'll be keeping an eye on it, and then we'll come back to those questions at the end of the talk. So I'm pleased to introduce Henry Beker, who lives in Windsor, England. Originally a mathematician, he spent many years working in informatics, building and growing companies worldwide. About 30 years ago, he became fascinated by mycology. Following a chance meeting with Danish mycologist Jan Vesterholt in 2000, he became interested in the genus Hebeloma. And that brings us to the talk tonight, which is really exciting, the Hebeloma project from database to website and AI-based species determination. And with that, I will hand it off to you, Henry.
Thank you very much, Alex. I appreciate that. And thank you to the BMS for giving me the opportunity to talk about one of my favourite subjects, which is Hebeloma. And thank you all to foregoing the barbecues this evening and watching the football in order to actually come and listen to a talk on Hebeloma. So that is also appreciated. So let's kick off, and I think start off with a little bit of music.
Nothing like a Hebeloma, nothing like a Hebeloma. Boys and pie in your eyes, nothing like a Hebeloma. Nothing like a Hebeloma, nothing like a Hebeloma. Boys and pie in your eyes, nothing like a Hebeloma.
Okay, well, we could carry on listening to the music, but I think we'll kind of stop it there. And my thanks to Larry Evans and Andrea Hassel, who gave me permission to use their song, which was recorded long before I ever got interested in Hebeloma. So nothing directly to do with me, but before I go any further, let me just make clear everything I'm going to be talking about this evening is very much a team effort. So there's a group of us who have been working together over a number of years, developing a real understanding of this genus. Numerous herbaria have helped us, numerous mycologists, and an amazing number of citizen scientists who've sent us collections and helped us along the way. So my thanks to all of them, but also my acknowledgement of all the effort that's gone in there. So why Hebeloma? Hebeloma are one of the most common mushrooms in the Northern Hemisphere in autumn. You actually find them sometimes also in spring, but in the Northern Hemisphere, they kind of tend to be everywhere in the autumn. They're also present in the tropics and in the Southern Hemisphere, but they're less common there. The Northern Hemisphere, they're very common. They are ectomycorrhizal, which means they're always growing in symbiosis with trees or shrubs, and therefore they're really a very important player in woodland and scrubland ecology, incredibly important. They're reasonably distinctive as Hebeloma. So most mycologists, when they're out in the field and they see a Hebeloma, they know it's a Hebeloma. But what happens then? They know it's a Hebeloma, but what do they do with it? And unfortunately, in the past, people have collected Hebeloma. It's one of those that stays in the bottom of the basket after they've sort of finished looking at all the, in quotes, interesting things that they found. So in the past, identifying Hebeloma used to be easy. People used to say, well, if it's small and it's got a veil, then it's obviously Hebeloma mesophaeum. If it's large and it's got a radishy smell, well, it must be Hebeloma synapisans. If it's got a very sort of sweet, sickly smell, it must be Hebeloma sacchariolens. And if it doesn't fit any of the above, then it must be Hebeloma crustuliniforme. And actually, if you go into probably 80% of all herbaria, or fungaria, perhaps I should say, and look at their collections of Hebeloma, you'll probably find at least 80% are those 4 names. And as for the other 140 plus species, they don't get much of a look in. By the way, I mean, the problem is they all look rather similar, and therefore identifying them is difficult. And that's one of the reasons also that people used to believe that Hebeloma were all ubiquitous. They all grew with any trees everywhere. We now know that's wrong. They don't. They're very specific. They're really good botanists in terms of sorting out their trees and who they love and who they don't. But to understand that, the first thing you have to be able to do is actually to identify which species you're seeing. So with Hebeloma, in 2000, I met with Jan Westerholt, who was a great mycologist, unfortunately died far too young. And he had been working on Hebeloma since the mid-80s. And he kind of introduced me to Hebeloma, and we started working together. And the problem we had was all the keys just didn't seem to work very well. All the descriptions you read of Hebeloma, every author had a different view of what each species was. And in the end, we decided the only way we could really attack this was we had to start all over. We had to start from scratch and see what we could do. And so we started in 2003, we started a database, and the database has gone through many changes, many iterations over the years. And these days, it's based on a system produced by Biolomics, BioWare, and it really is a very powerful database that we're now using. On this database, we have more than 10,000 Hebeloma collections. And what Jan and I decided way back, more than 20 years ago, was what we had to do was to find a way we could really compare different collections and start to understand the variations within a species and so on. And so the idea was to build a database where we could enter all sorts of information, paratromized descriptions of both the macro characters and the micro characters. And so that's what we started to do. And then Ursula Eberhardt got involved with us, and we started to sequence all the collections we had. So when you look at our database now, as I say, well over 10,000, almost 11,000 collections on there, all of them where we had permission and were able to are sequenced at least for ITS. And for some of the collections, in fact, the majority of them, we have several different loci, different genes that we have sequenced. So we really do have quite a good understanding of the molecular morphology, if you like, of these species. Included within those collections are almost all types. And that took a number of years to basically go around the world and collect up all the types that we could study, put the information on our database, sequence them where we could. But almost all types, there are a few missing from Brazil and 1 or 2 that couldn't be found. But otherwise, all of the types of all of the named Hebeloma species are all on the database. And that's kind of important. So now what I'm going to do is I want to swap across and actually take you straight to the database and show you the database. So I'm just going to switch this across and switch that down and bring up the database, which is there. And now this looks really complex, I know, but you don't need to worry about the detail here. What I'm going to do is just kind of give you a little bit of a feeling for what is happening here on the database. So the first thing that I'm going to point out is if I come right down to the bottom left-hand corner here, and hopefully you can see it, that's telling you there's 10,941 collections on the database. And essentially each line here represents a collection. And on the left-hand side, what you've got is just a kind of summary sheet there with each line being a collection and the names that we've assigned to those collections. And then on the right-hand side is the detail that goes into that particular collection. So here we have one collection called Anani, And maybe what I'll do is jump straight to the pictures. And if I just click there, that's what that collection actually looks like. So that row on the database is just that one collection of Arnony. And I'll come back to those pictures in a moment. If I just show you one or two other things, under general data, we have a lot of the metadata. So things like who collected it, where it was collected, the latitude, longitude, any information at all about the kind of habitat, the potential associated organism, the tree or the shrub that it was growing with, all sorts of information like that. That's the kind of metadata that's in there. And as I say, this we're talking about for every collection. If I pull that up for a moment, so we can go down, and there's all sorts of other stuff. There's all sorts of stuff about sequences that we have generated. But if I go into morphology, there's macroscopic and microscopic. So macroscopic, for instance, there'll be some general stuff. There'll be a description of the pileus, the colors, the shape of the pileus, the margin of the pileus, the characters there. If I go into measurements, there'll be all the sort of measurements for the fruit body itself, the basidiome, all sorts of stuff there. And if I go into microscopic, then there'll be all the measurements that have been made. So for instance, for this one, the spores, if I just pull down here, we actually measured 109 spores. And bear in mind, we have automatic systems for doing that. Otherwise, life is too short to be measuring 109 spores one by one. So you've got the spore count, and then you've got all the statistics associated with that. So the minimum, the maximum, the 5% to 95% range, the average, the median, all that sort of stuff is there. And it's there also for the Chylocystidia, for the Basidia. All of that is sort of measured and taken into account and recorded for that collection. And it also means then, if I come back to these pictures, for instance, if you want to know what the Chylocystidia look like, there you go, and you can sort of jump in and see pictures of the Chylocystidia. So all that information again is there in the database. If you wanted to know what the spores look like, let's have a look at some of those in Meltzer's maybe. Oh, let's look at the ornamentation in Meltzer's, or if I just look at the spores themselves in Meltzer's. And there they are, different magnifications. These ones that we use to do a lot of the measurements on, I'll just find it there. These will be 1600 times magnified. And we take a number of pictures, and then all the measurements are made off the pictures. So that is happening there. As I say, for every collection, this is happening. So we have all this huge amount of information, all these pictures stored in there. So let me just again emphasize, we're talking about nearly 11,000 collections. Every line is one collection. Every collection has all this data associated with it. So that is the collections that we have there. And then I'm going to jump over here to another table in the database, which is the species table. And let me just kind of order them alphabetically to make life easier. So here, what we've got is a list of all the species that have ever been named. And if you look at the bottom again, that tells us there are 880 published names of Hebeloma. Obviously, a lot of them are the same species, synonymized and so on, but there's all those species there. And if I take any particular one, like Arnony, because we were just looking at one collection of Arnony, in the species table, what we have is all sorts of information about the original diagnosis, any commentary, any information about the molecular, the sequences, and so on. But importantly, if I come down to the morphology, here what it's done is it's gone through the database, all the collections, and it's taken all those where we've named them as Arnony, and it's amalgamated them together to form one description. So we're forming a species description actually based on real collections. So this isn't sort of finger in the air and deciding what kind of rate. This is actually based on real collections. So here, if I look, I don't know, let's look at the macroscopic for a minute. Let's look at the measurements. Let's take the pileus diameter, for instance, the diameter of the cap of the mushroom. That gives you the range that we have measured across, in this case, if I look at it, it's more than 140 collections of Arnini that were on the database there, and they've all been amalgamated. That tells you the minimum we've ever measured is 17, the maximum is 170 millimeters, and then there's a 5% and 95% in average and so on. And those, we're going to look at the website in a moment. You're going to see those same numbers reappear there in terms of bringing all the information together. If we look, for instance, at the spores again, if I look, for instance, I don't know, spore length, what you're seeing here is a set of statistics based on more than 140 collections, where it's just all being pulled together as a set of statistics. So, as I say, the database has all this information sitting there. What I now want to do, if I can just simply get rid of this for a moment. Let me do that, let me just see. I don't need any more, so I'm going to close it for a second. I'm going to sign out of that. Okay, and then what I'm going to do is jump to the website. So we've got the database there with all these collections, with all these species descriptions that are an amalgam of all the data coming from each collection. And now what we've done, and I'll show you in a moment, is we've pulled that all together into the website, into hebeloma.org. So if you come onto hebeloma.org, you can all go onto it this minute if you want to. You'll find on there, there's all sorts of sort of background information, which I'll come back to later. But importantly, all the species descriptions are here. So these are all the species that we consider as being current. In other words, names we should be using today. And there's more than 140 of them. And we were just looking at a collection of Arnini. We were looking at the species Arnini. So if I click on the species Arnini here, what you'll see at the beginning, as you look at the website, is first of all, there's the kind of nomenclature information about the type. And by the way, if you want to, you can click on anything and just jump there. There's the original diagnosis. There's various references. So for instance, if I want to see what Mycobank says about it, I can just simply jump there and see what Mycobank has to say about Hebeloma Arnini. And then comes the description. So here we have, on the database, there were 144 collections of Arnini. And those were all amalgamated into the species description, and that's what you're seeing here. And what we've tried to do is to turn the kind of hard to digest information that's on the database into something far easier to digest, which is more sort of normal prose and the kind of description you're used to. But bear in mind, what you're seeing here is a description that is an amalgam of all those collections. So for instance, if you can remember the numbers we saw the pileus range was 17 to 170 and the 5% to 95% percentiles were 23 to 104. And that's what's reflected here. And when you look at this description, everything in black is kind of boilerplate, that's sort of standard there. Everything in blue is coming directly from the database. So in other words, that's just being mapped across, being put together from that species description and try to put into a slightly better English, but it's basically being mapped across from the database. So if you think about it, what is happening here is every time we make a single change on the database, we add another collection of Arnini, this description will get updated. And it all happens automatically. It's all just going on in the background. I'm exaggerating slightly there. It could be, but at the moment, actually, what we're doing is we press a button to update. And that's just because we're still in early days of this. And therefore, we like to kind of keep an eye just to make sure everything's updating fine and there aren't any glitches appearing. So here we have the description that's coming from the database. And remember, because this is coming from a set of collections, and in this case, and in many cases, a number of collections, what we've done, when you see words here, you see words like often, rarely, occasionally, usually. Here they have real meanings. So if I just open that up for a second, usually means it occurs in at least 80% of the collections that character is there. If we use the word often, it means it's between 50 and 80% of the collections have that character. Rarely means it's somewhere between 0 and 15%. The words actually have real meanings because it is based on a set of collections where we know what the statistics are. The other thing that's important is for every species, here we're looking at anemone, for every species it's going to look exactly the same. In other words, it's the same characters that are being described for every species. So here we have the macroscopic description, we have a microscopic description, particular emphasis on spore measurements and chylocystidea measurements. And again, bear in mind when we're talking about the spore length, we're talking about all the spores measured across 100, in this case 144 collections. So, you know, we're getting some statistics that are actually meaningful here. And also the range of means, the range of medians, the standard deviation. So all sorts of games you can play with these statistics if you choose to. But they are all there and all produced. And as I go down through the species description, the same thing is true with the habitat. So these numbers are real. So anemone was recorded of times where only one associate was recorded, 59.3% of the time, it was Salix. And then there's some other information about, you know, which families were recorded most often. But again, these are all statistics coming from 144 collections. And similarly with regard to the distribution that is described here as to which countries we've collected it in and so on, this is all coming directly from there. Some commentary, and then a distribution map. And this is an interactive distribution map. And so, for instance, I don't know, this one looks a bit odd here. If you want to, you can just click on it and it will take you to that particular collection and you can have a look exactly what was going on there, where it's collected and so on. These interactive maps are actually very useful. We've been looking at anemone up till now. Let me jump to a different species. Whoops, other species. Let me jump to something like Alpinicola. Alpinicola is a species originally described from North America. It's got lots of synonyms, as you can see. It was redescribed many, many different times. If I jump straight down, as you see, everything's the same sort of format, the same characters described. If I jump down, though, straight away to the... Now, this species is called Hebeloma alpinicola, which kind of gives you the impression maybe there's something about it that likes mountainous areas. And yet, here it is all over the place in Europe and in America. It's kind of interesting. You start to zoom in and you can start to see actually where they are. And they are exactly where you'd want them to be in a kind of funny way. They are up in the mountains and yeah, exactly where you'd expect in some sort of senses. So yeah, so the maps are quite useful, quite important. Let me just come down some of the other things we've got here, phenology, just in terms of when it was collected, so you can see in different continents which months it was collected in. And then a list of all the cited collections. So here, in the case of Alpinicola, how many collections have we got? Let's just go back up. 158 collections here. They're all on that map there. And here are all the details. And again, If there's any particular one you want to look at, you can click on it and go and have a look at it. Lots of collections there. And then you come to pictures. So again, for every species, there's a gallery where you can look at pictures of it. And there'll be quite a few pictures there to look at. If you want to, for instance, look at the spores, there's some pictures of spores. There'll be at different magnifications and different preparations. If you wanted to look at the Chylocystidia, let's wait for it to load. There we go. And then you can see the Chylocystidia of this particular species. So again, all the pictures are there. And this is true for every one of these species descriptions. If I go to another one, and yeah, by the way, you can go into any individual collection and see it as well. But if I go into other species, for instance, if I look at something like Hibernium, which I'm going to be looking at later, again, all the same things are there. Where the original diagnosis here was in Latin, there's a translation for you, all the links, the descriptions, the map. This one is ubiquitous across the Northern Hemisphere. Come down. Again, lots of pictures of the species. You can scroll through if you wanted to look at the Chylocystidia, for instance. Again, we have to give a moment for it to load. There they are. There's the Chylocystidia. And so it goes on. So for all these different species, we have that here. Okay, so again, just to kind of recap for a moment. So we've got the database with all the individual collections on there. Within the database, we've amalgamated all those collections to form species descriptions. And by the way, I should hesitate there, so I'll pause there for a moment and say, with each of those collections, the way we have identified it is by using sequencing, where normally it's several loci that we've actually used, several different areas of the genome that we've sequenced, and also we've used the morphology. And I go back to the point that on the database, we have all the types, or almost all the types from all over the world, and therefore we can make real comparisons because everything is parameterized. I can do all sorts of things on the database, like saying, you know, show me all of those that have a spore length on average between 10 and 12 microns, and it will just pull them all out, and then I can say, okay, show me those where in Meltzer's they turn a very dark cut, and so on. So I can group things together. I can, where we're getting clades forming, when we look at the trees based on the sequences, we can put all of those in a clade together and see how the descriptions, if you like, match up, how the spore sizes, the Chylocystidia, the pileus colors, all sorts of things. And so we've used all that information to actually determine the species, and then we've built the species descriptions. So we really have gone back to basics, starting with the types, sequencing them where we can, doing descriptions of them, macro and micro, and then building up from there. So, as I say, on here we have all these different species on there. All the species that are currently published are all on here. And if I go back to here, I mean, you may scroll down here and you may know, oh, well, hang on, what's happened to Hebeloma dunense? I thought that was a good species, but it's not appearing here. Well, I can simply go back and look up all published names, which is up there. That'll be all 880 of those names that have been published. And let's look for dunense. And there it is, there's Hebeloma dunense. And it tells me here that it's now been synonymized with velatum. And if I want to know more, I can have a look, and there's the original diagnosis and its translation, and a commentary explaining why it's been synonymized with velatum now. All the information will be there. So, you know, if your favorite name doesn't seem to be in the species list, you can always go back up to this all published names and search for it there. In terms of the morphology, there's also lots of description here, which is just all good sort of background information. Just take a moment to load there. So you can read all about the morphology and how you do things and so on. I now want to move on to this area here, which is the tools. So on the website, we have, as well as building all these species descriptions, we've made available a number of tools that allows the user, I'll use the word play, with the different characters and the different species and so on. So let's have a look at a couple of these tools, and eventually I will get to the AI bit, which is the identifier, but I'm going to start here with the where. So this one basically is where have Hebeloma been collected. So for instance, if you come onto here, you may say, well, obvious place to start is, let's look at Europe, and I'd like to know all the collections from England. Okay, you search, and it comes up with, here you are, there's 42 species that have been collected in England, so we know that all of those are good species for England, and there's the list of them, and there's also some examples, and basically it tells you of the number of collections we have of that species, how many of them were collected in England. So you can see whether, you know, it's kind of, you know, one of its favorite habitats, or it just happens to occur here and so on. So Ingratum, 1 out of 112, is probably not its favorite habitat, but it has been collected in England. But you may say, hang on, what about the British Isles? So I don't want just England, but let me add in, and you just do it in the usual way using the control key. So I'm going to add in Ireland and the Isle of Man, why not? And Scotland and Wales. And again, click on the search the collections. And it tells me we've got 48 from the British Isles. So we had 42 from England. There's another 6 from other parts of the British Isles. But you may want to be more precise than that. You may say, okay, well, fine, but I'm actually collecting in dunes at the moment. So tell me, how many have been collected in dunes? Which species have been collected in dunes in the UK? So let's search again. And 12 have been collected in the British Isles in dunes. And again, there's the list of them and some examples and so on. And you can just click on any of these, or you can click on to look at the species. And again, you may want to be even more precise. You may say, well, hang on, I've just collected this one in a dune, but under Salix. So what's been collected under Salix and in a dune in the British Isles? And again, there's your list. And you can do this for basically any region in the world. I mean, you can play games of this type and try to see. So for instance, I say, if you've actually just collected a Hebeloma in the dunes under Salix in the British Isles, then you can kind of compare it immediately with what else has been collected there. All that information is there and available. And as I say, you can simply kind of reset this if you want to, and look for everything collected under Dryas or everything collected under. There are many different ways you can do searches. Essentially, you're searching the database. You're doing it on the website in hopefully what we think is a reasonably friendly, user-friendly way of doing it. Okay, so that's the where tool. Let me now move on to one of my favorite tools, which is the plotter. Okay, here's the plotter. What the plotter enables you to do is to compare species or sections or different parameters. And so we kind of give you a feeling for that. So I'm going to do a couple of plots. So I don't want to compare two species. So this one I'm going to set to none. So get rid of that one. And here I'm going to do something I suppose in a sense is quite silly, but it doesn't matter. I'm going to just do all. And what I'm going to plot, the first one I'm going to plot is I'm going to plot on the x-axis, I'm going to put latitude. But on the y-axis, and by the way, look at all the different things you can plot, but I'm going to put spore area. And now I update, and it's immediately produced a plot that's showing me on the x-axis latitude, and on the y-axis it's showing me spore area. So what is that telling me? Well, it's telling me this line here is the kind of line of best fit. And it's telling me that as the latitude goes up, so on average, the spores are getting bigger. Which maybe we knew, but there's interesting evidence for it here. And we can immediately see it in a kind of picture form. We can see that. And as I say, there are lots of different parameters you can plot. So what happens when latitude goes up? Well, when latitude goes up, normally temperature goes down. So, for instance, rather than latitude on the x-axis, let me, for instance, say, I'm going to look at temperature, where I'm looking at the maximum average monthly temperature. So instead of latitude, I'm now looking at temperature and update it. And what have I got? Again, there's the line of best fit. And again, it's on a slope. By the way, these numbers down here are telling me how significant that slope is, whether I should believe it or not. And these numbers here essentially say, yes, it is very significant. And what this is showing is as the temperature now goes down, the average spore area goes up. Which is, again, it's interesting. And as I say, you can play this with any parameters you want to look at. And we have rainfall on there, we've got temperature on there, we've got all sorts of things. Here, perhaps what might be interesting is normally, for a lot of people, the definition of the Arctic is where the maximum average monthly temperature is less than 10 degrees. So if you sort of drew the line up there at 10 degrees, that's saying all those to the left of that, you might consider as being Arctic collections. And again, by the way, any one of these you want to look at, there's one up there that's kind of way out in terms of size. You might want to have a look at that. And then not surprisingly, Hebeloma grandisporum. And if you look at where it's collected, yeah, it's been collected in the Arctic in Canada at 72 degrees north. So as I say, you could try all different things here in order to kind of get a feeling for and an understanding for the different parameters, how they relate to each other. And as I say, you can also compare different species. You can, as I say, there's almost no end to the things you can do here in terms of playing games with it. You can work with sections, you can work with all sorts of stuff. Let me do something else that's kind of silly but fun. Again, I'm going to look at all, which isn't quite accurate, but doesn't matter. It's good enough for what I'm doing here today. And what I'm going to do is plot on the x-axis year, and on the y-axis, I'm going to plot day of year. Update that. And again, we've got a slope that is highly significant. And what this is telling us is that as the years go on, we are collecting it later and later in the year. The day in the year where we're collecting it is later. Is that down to climate change? Well, we can discuss the cause and everything else. That's another subject. But this is just pure statistics in terms of showing us that it is being collected later every year. And Interestingly, that's just a linear fit. If we were more accurate there, you would actually see that it comes along reasonably linear, and then around the year 2000, it really starts to take off. And the movement towards later in the year really does accelerate after the year 2000, which is, again, kind of interesting. So this plotter under the tools can be really quite interesting. And we have done quite a lot of work there with different statistics and so on. I'm hoping maybe later this year, beginning next year, we'll publish some results there. But there's nothing to stop anybody playing with this. And as I say, you can just plot different things against different things, choosing your own axis. Essentially, in terms of, sorry, not species, but in terms of the parameters you can plot, you can look at the spores, the Chylocystidia, the Basidia, basically anything that's got a numeric value, you can plot. So that's kind of fun, kind of interesting. And, you know, with almost 11,000 collections on there, there is actually some meat to it, as it were. There is something you can get your teeth into now. The statistics are starting to be meaningful. Although I should stress that, you know, for some species, as you saw, we have a lot of collections, but there are other species, like some of the tropical ones, some of the Southern Hemisphere ones, where we don't have that many collections yet. And therefore, with those, you just have to be a little bit careful in terms of whether we really yet understand the variation that occurs within those species. Whereas something like Arnony, we've got 140 plus, or Albinicola that we looked at, 150 plus collections, you can start to have some confidence that we're understanding the variation that exists there. Okay, so let me now come on to the identifier, which is another one of these tools here. So let me just go to the identifier now. And the idea here is this replaces, in our view, a conventional key, in that it's based on AI, machine learning. And what we've done is we've used the collections we have, and I'll say more about that in a moment, to train a machine learning algorithm that then helps you, or can help you, to identify a species, a collection, 2 species. So what have we got here? Let me try and explain it first, then we'll look at some examples. So the characters it's going to want you to fill in are just here. This bit up here is an autofill. So if it happens to be a collection that's on the database, you just click that and it'll autofill it for you. But if you've got one in your hand that isn't on the database, then you need to fill in this information. It's not a huge number of characters that you're going to fill in. It's a relatively small number. And let me explain what they are, and then we'll explain why those characters. The first thing we want to know is where you collected it. So latitude, longitude, and altitude. And that already starts to give some clues with regard to what it is. The only macroscopic character we're asking for is the number of complete lamellae. So in other words, lamellae, gills, if you like, that run from the stipe, from the stem, all the way to the edge of the cap. So what's needed is to count those. Now, do I always count them? No, what I normally do is I count a quarter and I multiply by 4, and that's good enough. Trying to actually count all of them takes a lot of work. And again, life isn't quite long enough. So one cheats a little bit. And that's normally accurate enough to sort of count a quarter and then multiply by 4. But it does give you an idea. And what's interesting with Hebeloma is that seems to be a very, very good, relatively consistent character, irrespective of the size of the pileus. So yeah, sometimes you get a few more of the pileus is bigger, but it doesn't change hugely. So most species have a range, and if we went back to the species descriptions, you would see there for every species there is a range of values for the number of complete lamellae that mushroom has. The next thing we fill in is some information about the spores. Okay, now the bottom three here are purely average length, average width, and average Q value. Q value is the length divided by the width, which you do for each spore, and then you average them. These are standard things that most mycologists who are using microscopy will do. You do need to measure, ideally, enough spores that you feel your average is a good average. We tend to measure a lot because we have tools to do it. If you're doing it by hand, measuring each one, you probably won't measure as many as we normally do. Let's put it that way. And then the other three things here are something that Jan Westerholt published a number of years ago, which was almost to try and get a measure of how ornamented the spores are, how dextrinoid they are, in other words, how much the color changes in Meltzer's solution, and whether or not the perispore is loosening, which is something that happens in a lot of Hebeloma species. When you put it under the microscope, you can actually see the perispore coming away from the spore itself, and a measure of whether that's just happening occasionally or whether you're seeing it on every single spore and so on. And if you go back to the Hebeloma morphology section, you can get a full description of how you estimate these three values, the OPD value. That, by the way, is being used for other genera now as well, not just for Hebeloma, but a lot of people are using it for other genera. It really is quite useful. If I move down for the Chylocystidia, the first few things are purely numerical. The average length of the Chylocystidia, the average apical width, and then three values, which are ratios of the average apical width over the width in the middle, the average apical width over the width near the base, and then the average value of the ratio of the base to the middle. So they're all ratios that you can simply work out. You can do it on a spreadsheet or whatever as you're measuring your Chylocystidia. And those are important because actually what they're doing is they're defining is probably too strong, but they're giving an indication of the shape of the Chylocystidium. All Hebeloma have Chylocystidia on the gill edge, and the shape is important. It seems to be a really important evolutionary character. And then finally, one question here, which is a little bit subjective, is asking you what you think is the dominant shape. And again, you can put in more than one if you're not sure, but it's asking what you think is the dominant shape of the Chylocystidia. Now, if you look at these characters you've filled in here, most of them are very objective in terms of where you collected it, the measurements of the spores, the measurements of the Chylocystidia. Really, the only subjective or more subjective characters are this OPD, the ornamentation, perispore and dextrinoidity, and this one down here with regard to the shape of the Chylocystidia. Those are more subjective. All the rest of them are pretty objective. And we did a lot of work, well, Pete actually did most of the work on this, did a huge amount of work on trying to decide which characters to use. And it's a trade-off. The more characters you use, the better the identification is going to be, but the more work it is for the person filling in the information, and the more it's going to put them off using it. So the balance was trying to find a relatively small set of characters that gave you a good enough result. And we'll see the results in a moment. The other thing that Pete found when he was doing this was a lot of the characters, particularly ones that are subjective, like the color of the cap, the color of the pileus, or how fibrillose the stem was, or a lot of those things were very difficult and didn't give good results because so many people had different answers even on the same mushroom. So they just weren't reliable as characters to use in this. And similarly, we did look at using associated organism, but again, we found that was dangerous because often the person collecting doesn't notice every tree that's around, sometimes gets them wrong. So again, we found that wasn't reliable either. Sticking as far as we could to these sort of objective characters that are purely measurements turned out to be much safer and gave much better results. So now, just before I show you examples, let me just say a little bit more about how this worked. Of our collections, what Pete did, because it was Pete that actually built this, what he did was he took the collections we had and he took 2/3 of them, and essentially he used that to train the machine learning. And that's what's called the supervised learning problem. Basically, he said to the machine, look, here's a set of characters, and this is this particular species. Here's another set of characters, it is this particular species. And he did that for 2/3 of the collections and gave that to the algorithm and said, now you learn and decide what is the mapping between the set of characters and the species. So for instance, if you take irony, it had 144 collections to work with, where it had the set of parameters for each of those that it knew was irony, and so it could work out what the mapping was. That meant we had another 1/3 of collections that we hadn't used that could be used for testing. And we'll come back to the testing later. So let me just start off by putting in a number here. This is a number of a collection on the database. Because it's on the database, all I have to do is click that and it'll automatically fill it in for me. So it's filled in all the values, the latitude, longitude, the altitude, the number of lamellae, the OPD values, the spore measurements, the kind of cystia measurements and ratios, and some information about the shape. And you can see on the map here, this collection looks as though it's actually from Belgium. And then all you do, having filled that in, as I say, I've cheated by it being one on the database, but you could just fill all of this in by hand. You press identify and it comes back and it gives you what it thinks is the most likely. And here it's saying it thinks there's a 58% chance this is a Bernium, 20% chance or 21% chance it's Alpinum, and then a much smaller probability that it's some of these others. But by the way, it's pretty confident that the right section for this within Hebeloma is the section or the subsection Passiliformium. Now, this particular collection, we know from our sequencing and everything else, we actually know it to be a Bernium. So it's got it right. But there again, notice this warning here tells you that that particular collection was in the set of collections that was given to the machine on which it based its learning. So in a sense, it's a kind of a little bit of a cheat, that one, because actually that was one of the ones it used in order to understand how to do the mapping from these characters to the species. Okay, so let's put another one in now. So this time I'm going to put in 17994. Press the magic button. Again, it's one on the database that's filled it all in automatically. This one looks as though it's sort of up in Alaska somewhere, certainly up on the north side of Washington or Alaska, somewhere like that, or the northeast coast of America. Press the identify and back it comes. Now this one has given us a 56% chance it's a Bernium, 20% chance of Alpinum, and again, much lower values for the others. Again, this one, it's almost 95% sure it comes from this section Passiliformia. And this one, again, our analysis tells you it is a Bernium. We've sequenced it, we've done everything else. And this one was not in the training set. So this one, it's done it for real. It's not one it knew. It's taken that set of characters and it's said that it is 55% confident that this is a Bernium. Okay, unfortunately, it doesn't always get it right. So let me just show you one where it didn't. Be nice if it did get it right every time, but it doesn't. Okay, this one, yeah, it's done it. Whoops, this one looks as though it's in France somewhere. Press identify. And here it's come up with Himali now. Himali 35%, Hibernium 34%. It's close, but we know from the sequencing and everything else we've done that this is actually Hibernium. It wasn't in the training set. It is Hibernium. It's got the answer wrong. And if I come back up here, and the first thing always is interesting is to look at the subjective characters. And the first thing I notice is here, it's got the chylocystidea as being either stipitate or ventricose. Now, for Hibernium, normally they're stipitate. It's rare to have many that are ventricose. If I change that, now look what it's done. Hibernium is now nearly 70% sure. Himali has dropped way down, which has this different shaped chylocystidea. So it is sensitive. And what I would always say is if you're using this identifier, then you need to be careful, especially with these subjective ones, the OPD and the shape. You need to be very careful with them. But if you're not sure, you can try different things. You could try it that way, and then you could try, well, I'm not absolutely sure, maybe it should be that, let's try it. Because it only takes a second to try, you can actually play games with it. The other thing I would say also is never just take, you've got to be very careful of just taking the first one. Now, I told you we can use, we use 2/3 of the collections to produce the algorithm, to produce the machine learning algorithm and therefore the AI identifier. What about the other third? Well, we'll come back into tools here. The other third we can use then to pass them all through and then compare with what we know to be the result and say, well, how did you do? And if we look at the result there, this is how it did. So this is on the third of the collections that weren't used to train the identifier. And what's that saying is if you look at the first guess that it gives you, you've got something like just under 77% chance that is correct. Not bad. If you look at the first two guesses, within those two, you're now up over 90% that it's got it right. And if you look at the top 5 it's given you, where are we? Then you're up about 97.5% chance you've got it right. So what we would always say is don't just look at the top one, that's important, but look at the top 5 it's given you and have a look at them and now go back to the species descriptions, go back and see, even check whether that's been collected in the same place before, whatever, but use that as a basis to go back and then, how could I put it sensibly? Use that as evidence towards trying to decide on the species. The other point that's interesting here is this graph here with the other is based on all species. So all 100, I don't know how many, 45 species that we have there. For the, as I mentioned before, some of the ones like the tropical ones and some of those from the Southern Hemisphere, we don't have many collections and therefore it is not as reliable yet on those. If you did the same graph, just looking at the Northern Hemisphere, which we've done, of course, then your probability here for the right answer being the top 5 would be over 99.5%. So it's, the percentage is actually brought down a little bit by some of these where we don't have many collections, where they're much rarer species, and we don't have enough collections yet on the database, and therefore with regard to the identifier. So coming back to the identifier here, It works very well, surprisingly well in our view, given how difficult Hebeloma are to identify normally. But it has its limitations. And what I'd say is don't just look at the top answer, look at the top few, and then go and do some work, some investigative work, and decide what makes sense. As a key, the nice thing about this is it changes automatically. One of the problems we had as we were developing keys was we discover a new species, and now we have to start all over again with the key. Or the species description changes because we realize there's more variation than we thought, and we have to go back. This is automatic. This key, if you like, is regenerating all the time. Every single new collection that comes on the database, the key is reformed. And that makes life much, much easier. So it's always up to date, it's always usable, and it's always based on the latest information. Okay, let me go back now to my slides, if I can get back there. Hopefully you can see the slide presentation again. So as we've said, we've seen the database with well, almost 11,000 collections on there, the parameterized descriptions, that almost all types are on there, that we've based that in order to do the synonymies, to do everything else. We've sequenced, I think, I can't remember now the numbers, something like 60% of all the types we have actually sequenced at least to ITS. So there's been a huge amount of work that's gone into this. And as I say, just bear in mind, 880 names, not all of those had actually typed material, but a number of them did. So that's been a huge amount of work to track them all down. And all that information is on the database. So you can go on to hebeloma.org and you can find all the types, everything is in there. So to summarize, for the approach we've taken, and certainly for a genus that is so difficult like Hebeloma, the systematic approach is absolutely critical. The species descriptions are continually evolving. As we put more collections onto the database, the species descriptions automatically evolve. We start to understand better the variation within a species and the limits between species and so on. And it means the species identifier is adapting as well as the species descriptions change, as new species are introduced and so on. It all just happens automatically. On the website, it allows you, as you've seen, the where tool, the plotter tool, all sorts of things you can use to explore the genus. So the AI species identifier we've developed, it shows a lot of promise, but there's a lot more to do. I mean, one of the things we are now working on is actually also putting a sequence identifier. So eventually you'll be able to say, I'm going to do with morphology, which is what we're there at the moment, or I'm going to do with sequences, or I'm going to do with both. And obviously the results, by the time we get to being able to do it with both, so with an ITS sequence as well as with the morphology, then the probabilities of getting it right are going to go much higher. It's going to be much, much easier to get good results. I feel as I've talked enough, so I'm going to stop now. And I guess I should probably stop sharing and hand back to Alex.
Yeah, that was amazing, Henry. My mind is blown. You can see how much your background in mathematics has really influenced your work here in mycology and how it's really enhanced it. That was really incredible, and it's big congratulations to you and all your collaborators on how much work has gone into this. It's very apparent. Our first question we have was from Louise, and she wanted to know if you were planning to expand this to any other fungal species.
Well, to other genera, I guess, is really the thing. Yeah, certainly in terms of species for Hebeloma, we're building all the time. We have about another 20 species we're aware of that we haven't yet published that will go onto there, and we'll just keep building it. But what we've done here, theoretically, you could do with any genus. There's nothing special about Hebeloma. In fact, we've published all the stuff we've done on AI, the algorithms we've used, everything else is published. It's all in the public domain. The problem is the amount of work to get the data. This has taken us, 20 years plus since I started working with the island, he had already been collecting and doing work for 10 or 15 years before that. So it's been a huge amount of work to collect the data. And the problem with all these sorts of things is, is the garbage in, garbage out. Unless you've got good data, it's not going to work well. And so that is the issue, is for other genera, is whether the data exists. And I think one of the things that's kind of sad is there are so many mycologists out there and field mycologists who do so much work and so many measurements. They identify and then they throw away all the information, all the data they've used to get there. And I guess what would be interesting, but maybe for somebody else to do, is if there were a way one could give them a database on which they could record all that information, then you would start to build up the sort of data that one needs in order to be able to do this.
On that note, have you requested, or would you like, if people are looking at Hebeloma, to send you data? Do you accept data in from field mycologists?
Yes, we do. And certainly we've got a lot of people all over the world sending us stuff. We used to have a rule that we wouldn't put anything on unless we'd actually seen the material and been able to do the measurements ourselves. Over the last few years, as more and more sequencing is going on, we've kind of dropped that rule. And so if there are good sequences, then okay, it may mean when the thing goes on the database, it doesn't actually have all the parameters that we would ideally like, but at least it helps with the maps and the distribution and stuff like that. So yes, I mean, we welcome that sort of information and we do put it on, yeah.
All right. We have a question here. Have you tried training the AI without subjective features at some point? And did that work or not work?
It's difficult to answer with yes or no on that. I mean, yes, it worked, but no, the results weren't as good. It does seem that the OPD, which is a little bit subjective, is really important. In other words, there's sort of description of the spore in terms of the ornamentation and so on. You could probably get away without the question about the shape of the chylocystidia. That improves a little bit, but not hugely, because those ratios that we've got there are pretty good for giving you an idea of what the shape is. And so that one, and the work we've done, we could drop that one. But the OPD, once you drop that, the results drop off.
Okay.
But again, I'd emphasize the importance of understanding that it is sensitive. And therefore, if you're not sure, is this an O2 or an O3? Well, actually, you could put in O2, O3, you can put both in. And if you're still not sure, you could even go back and say, well, now let me try with O4 and just see what happens, and do the results change? The good news is it really is just a click of a button to see the results. They are almost instantaneous, and so you can afford to play games with it a little bit and just see how sensitive it is on your collection with your parameters.
It's pretty incredible how quick it was. I was surprised how quick it could adapt to what you were clicking. We have another question. Marco asked, did you consider experimenting with some sort of automatic color coding in order to make the color characters less subjective?
Yes. Poor old Pete did a huge amount of work on that. We really thought that was going to work. And he did a lot of work in terms of trying to use RGB colors and all sorts of things like that, and giving it ranges and so on. And we never got good results. But he really tried very, very hard. And if anybody wants to look at the detail of that, I can put them in touch with Pete. And yeah, I mean, we spent ages on it because we were sure it was going to yield good results, and it never did. And we did find huge subjectivity in terms of people's. I mean, the problem with Hebeloma, they're basically all brown. Yes. I mean, it's just shades of light brown through to shades of dark brown or reddish brown or whatever. And yeah, it's difficult. So yes, we tried, and yes, we failed.
Well, that's just as useful as knowing what worked. Kind of on the same vein, someone was asking, have you tried using the machine learning to analyze microphotos? So just putting in pictures from a microscope and letting the AI work?
No, is the short answer to that. And I think that could be pretty successful. But no, we haven't done it. We have done some work with macro photos,
Okay.
and it's not very good. It tells you it's a Hebeloma. Well, that's pretty useful, but it's very rare that it will actually get the species right with macro photos. With the micro, the problem is, I've got a feeling if we did it with our photos, we'd probably get quite good results. But how easily that would translate to somebody else's photos, using different camera, different optics, different magnifications, I've no idea, but we haven't tried.
Yeah, I think that sounds like it'd be complicated, but interesting.
Mm.
We have a question from a field mycologist from John. How many Celiocystidia should ordinary mortals measure? So if you don't have the nice computer tools to do it for you.
Let me tell you what we do. And then for the apex, because the apex, when I'm saying apex, I don't mean right to the top. I mean, if you look at the top third, the widest part in the top third, for the apex measurements, we tend to do about 100. For the rest, we do about 20. So the others, we do all the measurements, sort of apex, middle, and base, and then work out the ratios and all the rest. We do that for about 20. My view is actually 20 for everything would be plenty. And probably with 10 or 12, you're getting pretty close.
Okay.
But it's one of those things where you need to kind of look at the edge of the edge of the lamella and see the Celiocystidae and see how regular they appear to be, and then make decisions about how many you really need to measure. But as I say, I think 10 or 12 you'd probably be pretty close. But we started off doing 20, and we always do 20. And as I say, for the apex, we started off doing 100. We cheat occasionally, but normally we try to do that.
Okay, perfect. We have another question asking, have you considered using computer vision, such as OpenCV, to make the counting of lamellae less arduous, such as using a photo and the detecting count? So I guess they're referring to you said you do it in quarters and multiply, but.
That's right. Yeah, I think that would work very well. We use software to do all the spore measurements and Celiocystidae measurements and the cydia measurements. We use software for all of those. We have a really good image analysis package from Leica. So for instance, we just give it the pictures of the spores and it finds them all for us and then measures them, which is why we can get things like area measurements as well as length and width and so on. All of these packages, they are getting better and better. And it's certainly worth experimenting with. But for counting the lamellae, I think that would work very well. It would take a bit of training. I think you'd have to, most of these software packages, you can kind of adapt them and train them. And I can't see any reason why that wouldn't work. Perhaps the only thing I could say about that is, again, it depends where you are and what you're doing. Normally, when we're out collecting, we'll be out for a week or whatever it is collecting. We don't have all our computer equipment with us, so we're having to do all the macro measurements kind of in the field or sitting in a hotel room or a student room or whatever it is, doing it, as opposed to having all the equipment around us. For the micro measurements, then we're in a much nicer environment, much more controlled.
Yeah, and that kind of brings up an interesting point that I think going to this talk, I had a bit of a bias against AI. I'm familiarized with a lot of people who are more maybe, they say traditional taxonomists who are very into doing everything by hand and a little bit skeptical of AI. And I think your talk has kind of highlighted that AI is great and it's a tool you can use as a traditional mycologist or a traditional taxonomist. And also that you need both. It looks like, you need the boots on the ground, you need the collections, you need people identifying, you need experts to work with the AI.
Yeah, and ideally you need sequencing as well. But But yeah, I mean, you need all of that. And as I say, even when you plug something into the identifier, yes, you'll get a result out, but then you need to actually look at the results that are coming out. It'll always give you a result. You need to look at the results coming out, go back to the species descriptions, has this been collected in the sort of habitat and environment that, there's still a lot to do, but it's a hell of a tool. And
Yeah, this has really opened my mind to that.
Yeah, it beats traditional keys. I mean, I hate traditional keys because you get stuck on one couplet and you're finished. Or you get one wrong, and you still may come out with an answer, but you're way off.
Yeah.
So yeah, and the thing I love about this is it adapts itself. So you don't have to keep rewriting the key. It's adapting itself all the time. But it is just a tool. It's a tool for the mycologist to use.
Yeah, I think that's a great way to think of it. There's two more questions we have that are kind of good ones maybe to end on here. We have one that's maybe zooming out a bit. How significant would you say that Hebeloma species are for the health of an ecosystem?
Huge, hugely important. I mean, they are one of the most common mushrooms that you'll find in autumn in the woodlands. Hebeloma, inocebi, Cortinarius, huge numbers of them all over the northern hemisphere. Just about any forest you go into, if you're at the right time of year, you'll find Hebeloma. If you go into the Arctic, I would argue they're probably the most common things in the Arctic, Hebeloma. I'm just wondering, it'll be a close call between Hebeloma and inocebi, but I reckon Hebeloma would win. But maybe inocebi specialists would disagree with me.
You might be biased.
Maybe. But no, they're hugely important. I mean, they're everywhere. And of course, they're also hugely important in some places. They're eaten as well. Now, I'm not recommending to eat Hebelomas, poison pie. There's a reason why that name is used. But there are parts of the world where they are eaten. And so, for instance, in Mexico, there's an interesting project there where they had a Hebeloma that they sell in the markets that they eat that's considered fantastic. But also, they found that this Hebeloma also helps when they have seedlings they're going to plant of trees. They inoculate it with this Hebeloma, and it encourages the growth. And when you see, the different growth of those seedlings that are inoculated with the Hebeloma versus those that aren't, there's just a huge difference. And so the project, I mean, it was a species that was unnamed. I mean, we named it, I don't know, 3 or 4 years ago now, but it was an unknown to science species. It was very well known to the Mexican people who were living off it. But they've got a project going where not only where they're replanting forests, they're helping the trees to grow, but they're also providing food for the locals.
That's amazing.
Which is great.
Yes, and you may have already answered it just now, but the last question was, do you have a favorite Hebeloma species?
Do I have a favorite Hebeloma species? No, I'm not sure I do, actually. There are certainly some that are very beautiful in my view and quite rare, and I always get excited when I find them. But that doesn't mean they're my favorites. They're just exciting to find. I mean, there are a lot of Hebelomas that are called corpse finders, or the ghoul mushrooms and things like that, because they like growing off cadavers, dead bodies and things of that type. And some of those are actually quite beautiful, very elegant mushrooms. And as I say, they're always a delight to find, but then trying to find out what they were actually growing off. And they're still in association with the tree, but clearly they love that extra nitrogen that's being produced by the decaying corpse. One little story, perhaps to finish on. I was up in the Arctic a few years ago, actually camping up there and going out and looking for Hebeloma and so on. And on one particular day, we went out in our 4x4s and sort of got up into what was almost like a desert area. It was actually a raised beach. What had happened, the area had been covered in ice. And then as the ice melted and therefore the weight disappeared, it actually rose. So although we were a long way inland, it it was actually beach-like. You know, there were shells, it was sandy, all the rest of it. And then as we were walking through this area, we discovered the bones of a whale.
Wow.
And around the bones of this whale, there was this little habitat, this little ecosystem that had grown around it, where clearly the mushrooms had grown there, that had encouraged the plants presumably to grow there. Animals started to come to feed there and were leaving their droppings behind. And in the middle of this sort of desert with nothing, there was just this little ecosystem full of salix and various other plants, and full of mushrooms. Again, many Hebelomas, but lots of other things as well. And it was just kind of so weird. But so beautiful, this little ecosystem in the middle of nothing.
That's incredible. You know, you hear about the whale bodies in the ocean becoming an oasis and a place where lots of organisms come to eat and thrive. And I guess we don't hear as much about that being on land.
Right.
So that's really interesting.
Fantastic.
Well, thank you so much for your time tonight. That was really amazing and interesting. And I hope this will inspire a lot of field mycologists to go out and look at the scary Hebelomas that a lot of us have been avoiding. These tools will make it a lot less scary.
Thank you very much indeed.
Yeah, so thank you, everyone. I hope you have a nice evening.
Bye now.